Hello students. So we will continue on vibration of continuous system. Yeah. Okay. So as I said, this is chapter number 7 in your ebook and chapter number 8 in the paperback. So last class we looked at the vibration of beam, yeah. So and we specifically looked at a beam, and because of the mass distribution, because of its stiffness, flexural stiffness, because of that there will be some vibration. Okay, and we got some equations, and from there we solved it, and we found out what is the natural frequency. Okay, a few things I missed out. Actually, I should specify basically, so that I will do it today. And also, like when you are saying like natural frequency, what is the meaning? So you will probably see that in the lab, but here also you can see this is the first mode. You know, so what you see here is the first mode. So first mode means the basic fundamental natural frequency. So this is a rod, this is a beam like this one fixed at one end. So this is like the cantilever beam, and then when you excite it, or you give the base excitation, you increase start from omega n equal to 0 and go up, you know, so vary omega n from 0. So meaning that you have this and you have omega n is equal to 0, that means static. Then you start moving slowly you are increasing omega n, and then there will be one omega n where you get this vibration. So this actually, what you are seeing right now is one kind of resonance you get at this frequency, you know. So this must be its natural frequency, and this is when you say mode, the first solution, you will get it will be moving like this. So it will go something like this. Yeah, so move like up and down. Like if you hear it will go like this one in one extreme, the other extreme it will be like this one. So it will move like this and this, right? It will go up, down like this one. Okay. Now so you keep on increasing. Okay, so we keep on increasing the natural frequency. So here we have got, which is the first one. Yeah. Now you keep on increasing, and then somewhere you will get another. Just see. Okay. You got some idea, yeah? So what you see right now is a little bit different. Okay, so how different it is? See here. So you are getting a node somewhere, you see. Somewhere in the middle, you see a node where things are not moving basically. Yeah, what you see is a stationary, and two ends you have that. Yeah? So this is the second natural frequency. And the second natural frequency, what do you get? You get, this is the original one. And the mode of vibration will be, it will start from here, go like that, something like this. You go like this one, and this is the two extreme positions. So this is what you see, one node in between. So this is first, this is omega 1, this is omega 2. This is first natural frequency. This is second natural frequency. and so on. There will be infinite. So second one will have 2 nodes. First has no nodes in between. Second has 1 node here. Third will be 2 nodes, and so on. It will keep on increasing. Yeah. So again, I'm going to show this mode of vibration. This corresponds to omega 2, or you will get, when you solve for beta, for example, beta will be in terms of n, because beta x comes inside sine or cos. Yeah, so if it comes inside sine beta x equal to 0, that means sine beta x will be equal to n pi, right? So hence you have n terms automatically there, right? So that n basically, so depending on if you increase n, hence number of nodes will also increase. So I'm going to show it again. This mode, first mode, you see here, there is a node is at the end only, means wherever we are fixing it, there. Now we keep on increasing, and then just hold on. See here. Yeah. So we get this is where the node you are seeing, right? So this is the node here. So this is the second mode of vibration. Similarly, if you have a machine, then you can even increase this frequency of the base excitation. You will see 2 nodes then, and so on. Then you can do. So basically, if you have one stick, flexible stick like this one, you can do experiment yourself to see that. The equation we used yesterday was like this: EI del 4y over del x4 equal to minus rho, then del square y, del t square, and then we assume y equal to product of 2 functions p and q, where p is a function of x only, q is a function of t only, like this. Finally, with transformation, what we got? We got something like this: 1 over p pi over p del 4 p over del x4 equal to, right, equal to minus rho del square q over del t square rho over q, and we called equal to c. Okay. One thing you remember that C could be positive or negative, right? Either positive or negative, and choose the one which satisfy the boundary condition. So choose one that satisfies the boundary conditions plus initial conditions, right? So that's what we have to choose. Okay. Now let us say yesterday for this equation, for minus rho del square q del t square over q equal to c, let us say, right? Now yesterday instead of writing this one like this one, probably I choose minus here, yeah, like minus here, plus here, like that, but doesn't matter. In any case, whichever the one which satisfies the boundary condition and initial condition, that has to be chosen. So I'm going to demonstrate. So if this is the equation where seriously we call it negative, I'm going to choose it. If that is the case, if this value is negative, yeah, so the solution, here if you see the final equation will be something like this: del square q del t square, and then here it will be c here, c q, so c it will be q over rho, sorry, so you get c over rho q equal to 0. So you get this equation. If this is negative, regardless of its negative or positive, let us say the solution of this will be simply e to the power lambda t, right? Let's put it here, okay? So what you get? You get lambda square here plus c over rho, yeah, and then equal to 0. Yeah? So if q, you get q equal to e lambda t will be a solution if you put it there. So you get lambda square, in fact will be q equal to a times this, yeah. So you have to find out a also. So if you put this value here, you get lambda square from here plus c over rho, and the q we get that is not equal to 0. So what we get finally is like this one. Now if that is the case, like this one, the solution will be lambda equal to plus minus root minus c over rho, right? And this is the solution. Solution will be q equal to a1 e to the power first one minus c over rho plus a2 e to the power root, this will be plus, this will be minus c over rho. Now if this is the solution, what do we get? From here, if c is negative, okay, if c is negative, then what you get? You get q equal to a1. Sorry, there will be t terms also, right? So we get a1, let's say e alpha t plus a2 e alpha t plus then minus here, where alpha is a real number, right? Real number, it's not complex, the real number, okay? Now q, since u equal to y xt, right? So yx0 will be 0. Let's say we are starting from that position, we call t equal to 0 when all of them is basically a straight line. Yeah, beam is a straight line, right? So in that case, y is 0 everywhere. If that is the case, you put it, that really means q t means you know y equal to px times q t, px times q0 equal to 0. That really means q0 equal to 0. That really means, yeah. Hence, if you put the q0 here, what do you get? Q equal to 0 here, 0 here, you get a1 plus a2. Yeah, that in that case a1 plus a2 equal to 0 you get. Yeah, okay. Now you have to do analysis further. What you see in this case is when you increase t, q will keep on increasing. Yeah, it's kind of not bounded basically, right? So it's with time this value will keep on increasing. Yeah, so this will tend to 0, but this will keep on increasing. That is not kind of vibration. This is not when you say vibration, when you're talking about the vibration problem, the value should be something which will come back to original position. So it will go up, beam goes up, comes back to original position, then goes down, up and down. So this is not the one which is representing the actual solution basically. Yeah. So with although it has satisfied one boundary condition, but doesn't mean that this is a oscillatory motion. You know, saying this is not an oscillatory motion. Okay. So this solution may be relevant to some other problem, but this is not relevant for the vibration problem. Yeah. So this is hence this will not be applicable to vibrations. Okay. So we can say that when C is negative, this is not working. Okay, so if C is negative, okay, so this does not represent Q is not oscillatory. Yeah, so this is not oscillating in time. It is not actually represents some kind of sinusoidal. So it should go increase then decrease, then increase and decrease. This kind of behavior is not captured because we had e to the power alpha t, where alpha is a real number, and t e to the power t, it will keep on increasing and increasing. Or we have with that we have e to the power minus alpha t, that will decrease and decrease and decrease. Okay, so combination of the two, we basically in long run, the one which has e to the power minus lambda t will be 0, yeah, and the one which has e to the power like alpha t, which will be dominating, which will be the one will be remaining. So let's write here that C is negative, Q is not oscillatory, is not oscillatory. Right? So we got that. Now second thing is like second option, when C is positive. Okay, in this case C is positive, then what happens? Q equal to A1 e to the power, here is minus, and C is positive. So what we get? EI alpha t plus A2, yeah, e to the power I alpha minus, like this one. Yeah. So what you get? Or in fact you can also write omega, basically that's what we actually got. So we get omega here and we get omega here. Now you can see that this is basically have the cosine term, the sine cosine terms comes into picture. Yeah, so this represent will be A1 cos omega t plus I sine omega t plus A2 cos omega t minus cos omega t minus sine omega t. Minus sine omega t, like that. Okay. So now what we see is a kind of oscillatory, like this is oscillatory, Q is oscillatory in this case, right? Again, when we have as a real problem in this case, actually this solution, when you have this del A square Q del T square plus C over rho Q equal to 0, where C is a positive number, then this is satisfied by Q equal to sine omega t. Both, in fact, sine omega t and cos omega t both. Okay. So this is general solution in complex format, but you can also choose just one of them, like sine omega t. You put it here, and you will see that this is going to satisfy. Yeah, and hence from here, if you put here, so it looks like if you have a Q equal to sine omega t, if you put it here, then what do you get? You get here you get a minus omega square plus C over rho equal to 0, or hence omega equal to root C over rho. So this is what you get automatically. So that means what we found, the bottom line is, whenever you are writing equation like this one, you have to test for both positive and negative, and whichever is oscillatory, whichever give you oscillation with respect to time is the one which is going to give you the results finally, right? So this one, since this is the Q equal to sine omega t, satisfy this one only when C is a positive number, hence you have to go with this positive number, and hence this also you have to solve with the positive number only. Yeah, so in that case you can. Yesterday we solved for both of them, and for both of them solution will be different. You will get actually different solutions, and from there also you can get a clue what you would see in, if it is negative, we got a different kind of solution. It was positive, we got different kind of solution for P also. So we will just look at that quickly. Okay, so now let's look at this one. So EI over P del 4P del X4 equal to C. Now if we take negative number first, then in any case, doesn't matter, we can just write EI of the solution. This will be del 4 P del X4 minus C over EI P equal to 0, and in any case solution will be here also equal to P equal to A e to the power beta X, right? And then we put it there, put it back here. What we get? Beta to the power 4, and then we get C minus C over EI equal to 0, and hence beta will be equal to C over EI, and then we get, this one is the negative, right? So now over 4, C over EI over 4. Now the behavior we can see from here. If C is negative, then what happens? Then what you see is beta becomes equal to I, and then you get, this is negative, right? So C is negative. So what we get? We I minus C over EI. Okay. So this is what we get. Again, there will be plus minus of that. So we get plus minus, then I, and then 1/4 of that also. Yeah. So we get that. Yeah. And then okay. So first, if beta will be equal to that, so just a minute, I think there is a problem here. So see here, write beta 4 equal to C over EI. Now C is negative, so beta square becomes equal to plus minus I, and then minus C over EI, and then we have half square root of that. Yeah, and then beta will be again plus minus I, and then we have minus C, then EI, half, and then half of that also. So what we see here is we will have some kind of alpha plus I beta type of equation. It is not a real just alpha, it is not just beta, but it will have both of them. So that means solution will be something like this: P equal to A1 e to the power alpha plus I beta x. So it will be A1 e to power alpha x plus e I beta x. This is multiplication here. So what you get is both multiplied. So we have e to power alpha x also, then multiplied by sine beta x and like this. So we have that multiplied. So it is not purely sine. So we have this also coming into picture. That represents that with time this will keep on increasing. Basically the amplitude of that is also kind of, this will make it unbounded basically, right? The way it did in case of the Q. So similarly we are getting like this one. So C here, C negative actually is kind of not working here also. But when we take C equal to positive, it will work here also. Yeah. So let's see C equal to positive. Then you have, then what happens? Yeah, same thing, but repeat with C equal to positive number. So C equal to positive number. Then what happens? Then you have beta equal to you have plus minus. Then you have C over EI, and then you have beta square. Then beta equal to you have I plus minus I C over EI, and then you have plus minus, like this, yeah. So this will be plus minus I 1/4, and then plus minus C over EI 1/4. Okay. So these are separate now; they are not together, right? So either you have a purely complex number or a purely real part. You know, so writing the solution will be P equal to A e to the power beta T beta x, and hence what do you get? You get, if you put this one, then it will be sinusoidal. So you get sine beta x. If you have cos beta x, if you have this one, then you get e to the power beta x, yeah. So plus minus. So hence you will have in this case you will have sinusoidal coming from this one e to the power I this value, yeah. And from here, so what I mean to say is finally you get sine C over EI, right, 1/4 of that x. Either you will get or cos of the same thing, or from here you will get e to the power C over EI 1/4 of that x, yeah. And then there will be another term which will have e to the power minus C over EI 1/4 and x, right. So we call this equal to beta basically, right? So or any number you can call alpha, let us say call alpha. So what we have, you have e to power alpha x, and you also have e to power minus alpha x. So if you write this equal to this one is nothing but this is cos, hyperbolic cos h alpha x, you call it, right? Or hence the in solution yesterday we used cos hyperbolic in terms of cos hyperbolic. Either you can write in terms of this and this, or you can write in terms of cos hyperbolic alpha x. So this is this one, and sine hyperbolic. So sine hyperbolic alpha x, that really means e alpha x minus e to the power minus alpha x over 2. Right? So this is sine. So basically either you write spell out e to the power alpha x a1 times this plus a2 times this, or you can say a1 times cos hyperbolic alpha x plus a2 times sine hyperbolic alpha x. So you can write like that. So all these clarification just to give details how to solve or finally get solved. Next thing only is if you have the equations for different kind of vibration, the method that we have used to solve this one, exactly you can use that to solve those. Okay. So now I'm going to present some equation for different vibration problems based on the continuous system, but I'm not going to solve it. Okay. So that's why I explained. So mathematics, you already had the partial differential equation. Here I'm explaining is just a repetition of that. Yeah, so you may be knowing better than me. Here my idea was to actually make it relevant. Okay, so how to solve it. So if you are writing like this one, what kind of C we are looking for? So is positive is relevant or negative is relevant, and we have seen automatically what's the problem. So what we have seen here, when C is positive, in this case, both will work. If C is positive, this we get as sinusoidal, actually, or the solution from here, this Q we get sinusoidal. And if C is positive, we also get this one as a combination of a sine, cosine, and hyperbolic sine and cosine, which are the solution, final solution that we used for that one. Okay, so that you have to remember. Okay. So as I said, now I will just derive differential equation. From there you have to solve, because now I assume you will be able to solve, and this will be as we solve the the beam vibration problem. Similarly, we can solve them also, and also this is given in your textbook, so you can also refer to that. Okay, so we are going to just derive, and from there you have to solve them. Okay, so next thing will be basically the axial vibration of rod. Axial vibration of rods. Okay, so what is the meaning of that is again you have studied already, and there may be a bar like this one. You have axial force like this, so this is the axial force P like this, and then if we know that if you apply, you have the you know the static, you have done the static analysis, but the idea is here now this has also a mass rho, so mass per unit length is given. Okay, this has mass now. So axial, you know that it has a stiffness. Okay, so we know K equal to EA over L. So those, but if like this, then it can vibrate also. So this is something like if this were very flexible, so that really means something like a spring, behavior like a spring. We just push it like this, and then it can vibrate, go like this. This is something like the spring basically. Yeah. So let's look at one element of that. So we have force. There will be force here. So we can write F instead of P, so that we don't confuse with this rho. So this is we have F here, and we can write F plus del F over del X. Okay, so this is from here to here, del X is there. Okay. So this is the only axial force only, but force may be different at different section, right? So okay, so this is like that. Now dynamic problem. What is the problem? We can write as del the summation of forces in the x direction equal to m delta m, and this is x. So the u, basically u is a displacement. Yeah. So u double dot. Yeah. So u is a displacement. Right? Displacement ux. U will be different at different location along the rod. Yeah, so this equal to this. So total force in that direction is nothing but del F over del X. So you have F positive direction, this minus negative direction F, and this is equal to del M. Del M is nothing but rho, right? Rho times del X is the total mass. Since this rho is the mass per unit length, so rho times del X. So we have rho times del X, and then del A square U del T square. So we have that. So finally, what is this and this is going to cancel out. So we have simply equation is a del F over del X equal to rho. Yeah, rho del square U over A square. Yeah. So this is the equation so far. Yeah. Next we have to write F in terms of U, because both the sides we have seen that if U is appearing here, U should appear here also. And how to do that? So F, we know that F equal to sigma times A, right? So this is stress times area. And stress we know is equal to E times strain. So E times strain times area. And strain we know equal to, we write EA, strain is equal to del U over del X. Yeah. So we know all those things we have done already during the solid mechanics class. Yeah. So we can write here. So del over del X, and then we have EA, and del U over del X equal to rho del A square U del T square. So final equation is, assuming EA equal to constant, your equation becomes EA del square u and del x square is equal to rho del square u del t square. Yeah, so this is the equation you get for the axial vibration of the rod, like this one. Now you can solve it the similar way, you assuming u equal to px times qt, and similar way you can solve the way you solved earlier. So solution method we know already, just you apply it and you will get the solution of that. Yeah. Of course, there will be some boundary condition that this will satisfy. Boundary condition and initial condition, both of them. One thing notice in this case is for the bending case we had del, here we had like power 4, means the derivative which was 4 time derivative, but in this case it's just double derivative only, del square, but there you had ei del 4. Yes, that's the difference. Yeah, so but when you had that difference del 4, you had also negative sign here, but in this case what you say, del square, here also here a square and there is no negative sign. So then you know that like assuming this equal to a negative value equal to minus some negative value will work for both of them. Not here, but when you have the final separated equations in that case. Yeah. Okay. Anyway, so this you can solve given your background, given your courses on partial differential equations, and also your experience with the first problem we solved for continuous vibration. Yeah. Now let's derive the torsional vibration of rods. Yeah, and how will you do that? This is again there may be a shaft here. It has its own mass, and you have degree of freedom is phi. Yeah, so phi is a degree of freedom. So we take a slice of that, and what do we get? We get there will be a torque. Yeah, so here there will be a torque T. Yeah? So torque T. I'm looking from this side. So torque T here will be like this. Will be T plus del T over del X. So this is del X. You have del X here, and this will be if this is like this one here, this will be anti-clockwise. Here will be clockwise. So these are the torques which are being applied there, and then we know that total moment or total torque, total moment in this is x direction, about x direction, has to be equal to j. Okay, where j is the polar moment of inertia, the mass moment of inertia here. Okay, so equal to j and phi double the, right? So equal to j del square phi over del t square. Yeah. Okay. Now, if you look at that, what we find? So total will be t over del x, right? Times del x also here into del x, minus t is equal to j del square phi del t square. And what solution we get? We get finally del t over del x equal to j del square phi over del t square. Okay, so we got that. Again we have to write this t in terms of phi. Okay, so how do you do? So we have to write the phi. How do you write the phi? So similarly as you did for the axial case, we have to do. So how will we do that? So let us say here you have till here it's phi, and from here to here you have phi plus del phi over del x over multiplied with del x. Yeah, and you know we know the torsional problems we have already studied during the solid mechanics class. So you may recall we had phi equal to T L over G. We call it J that time, but J we have the different meaning now. Here J means mass moment of inertia, mass plus moment of inertia. You will write IP. This is the polar. This is polar second moment of inertia, second moment of area. Moment of area. You used to call J during the solid mechanics class, because J we never used as a mass moment of inertia, so that's why we used like that. But here instead of J we are using IP. So this is about second moment of area. This is the moment of inertia, so second moment of mass basically. So that's the difference. So okay, so now difference, if you see from here to here, if you go from here to here, the difference del phi difference will be equal to T times L. L from here to here is del x only. So this is del x by G over IP. So assuming T is constant from here to here, you know, so the amount by which it will twist, the change in the twist for phi, del phi will be equal to T times L. L is the total shaft length, but in this case shaft length is just del x, so you have del x here over G times IP. Hence you get del phi over del x times G IP is equal to T basically, right? Okay, and same thing we are going to put it here, and hence we will get del over del x, and instead of T we will write it like this: G IP del phi over del x equal to J del square phi over del T square. Or in other words, when G and IP are constant, so we write G, where G is the shear modulus, remember? So IP del square phi del x square equal to J del square phi del T square. So this is the equation. Again, this equation is exactly similar to that we obtained for which case? For the axial. Yeah. So we get the exactly similar. So instead of E we get G, instead of A we get IP, instead of here we have there we got rho. Yeah. So instead of rho we get J in this case. Yeah. So that is the difference. Now, when we are writing J, there was some problem. J will be the small delta J, I would say. Yeah. So when you say delta J, that really means we have to write rho delta J. Yeah. And for the small section. Yeah. So that really means what? So if it is for a small section, so if it is a rho, and then we have we can have a radius of gyration, we can write so how do you find out? So that J will be dependent on rho basically. Yeah. So this delta J, instead of we should have written delta J in, here. Yeah. So where delta J will be for this one, right? For this one, so like this one. So this will depend on it will be equal to mass times radius of gyration. Yeah. So where mass will be rho, which is the mass per unit length, yeah, and then del x term will be there, yeah, del x term will be there, so hence del x term will be cancelled. Okay, so there was a mistake here, and then you will have some value here, so rho and then times del x then k square. So what you get, actually rho k x square term will be there. So just we write here rho kx square. Yeah. So okay. So everywhere we write like that only. So we write rho times k square. So to understand that here k square is a radius of gyration, yeah, of the section. Yeah. So k is the radius of gyration. Radius of gyration of the section. Yeah. Okay, so this is how you get the equation, but the idea remains the same. Instead of rho, you have rho k square here, and instead of E, you have G, and instead of A, you have IP, and instead of phi, instead of U, you have phi here. So the solution, the type of solution you get there, type of solution you get there also. So theory of vibration is not complete without the musical instrument. Yeah. So guitar, basically this has strings under tension, and because of different densities, mass per unit length, and they will have different behavior. Okay, even if the tension is the same, because of the mass density or the mass per unit length of this string, this will have different vibrations here. So although vibration we are studying, it started actually with the continuous like a system. So this what you see here is all continuous. These strings are continuous, and actually history actually starts vibration theory of vibration history actually starts with this music basically. So Pythagoras, for example, we know for mathematics, so you think that since he was a mathematician, he would know about anything about the vibration, right? So, but actually he was, he would not involve into music and all. So actually it turns out, actually he was the one who was the first to study the vibrations. So he played with different kind of strings under tension. He gave some, some tension to the strings, then tried to play it, and then he saw different musics. Actually, he made some musical instrument. He actually also gave some music theory and all. Yeah. So this why am I showing this one? Because this is the next one we are going to talk about, the string under tension. So what kind of vibration it has. Yeah. Okay. So we will start. There is a string. Let us say this is a string like this one. Yeah. And then under tension. So we will take one part of that, like something like this one. Then you have tension here, tension here. So this is T. Here tension T plus del T over del X, del X. So here from here to here, you have F, del X. Here T is tension, not the torque, it's tension. Right? Okay. Now we have to write the equation for that. So we say this is theta, right? From here to here, this is theta. Yeah. Okay. Now if this is the theta, very small length we are actually taking. Yeah. So what do we get? We get some equation, And what kind of equation will we get? So total force, total vertical force F y has to be equal to whatever mass of this one is, delta m, times we have del square y and del t square. So this is what the equation is. So what we are going to assume is tension remains the same throughout. So tension is the same, okay, tension does not change. However, theta is changing. So here we have theta, and then plus we have del theta, and then we have del x. This is the best. Yeah. So now we have to see the vertical components. What we see here is the theta is small. Okay, theta is very small. We will assume that. So what do we get? We get all the vertical forces. So in positive direction, we get t, and then we get cos here, so sine. So sine theta plus del theta over del x. Okay, so that is the direction. Minus we get t, and then we get again cos this one, the sine here. So sine theta will equal to delta m. Delta m is nothing but rho. Okay, rho and del x. So this is del x. Okay, so del x, and then this becomes delta m, del square y over del t square. Okay, now next is since theta is very small, so we get t times theta plus del theta del x times del x minus t theta equals to rho del x del square y del t square. Next we get this, if we simplify, we get t times del theta over del x equal to rho then del square y over del t square. You know that theta equal to del y over del x, so put it here. So what you get is t times del square y over del x square equal to rho del square y over del t square. So this is the equation which is followed by the strings under tension. Yeah. So what you get is like this, or del square. Actually, that's it. In case of axial load, what you get? You get here E times A. So instead of E times A, you have the tension T. Here you had rho. Instead of U, you had Y here. So this is what the equation is. Yeah. And then apart from that, there will be a boundary conditions. Right? So boundary condition will be if there is a string here between this and this. So x equal to 0, x equal to L. Okay, you will have y equal to 0 and x equal to 0 and x equal to L, for example. So these two boundary conditions you have. Then you will have initial conditions as well. So initial condition will be for example y x t equal to 0 equal to all 0. So that will be the initial condition. Okay. So this initial condition, or if you have a string like that, like in guitar, you have you pluck the one like give some kind of impulsive load to the string, right? The string under tension, and after that it is a vibration. So you have a string, you have pulled it, so that may be the initial condition. So everywhere you can give what is the value of y. Everywhere velocity will be 0, but there will be y at everywhere. So from there also you can go and you can solve the problem. So in any case, so we have these equations now. In all the cases, you have the equations next thing is to solve, and you can solve as we have discussed already. Okay. So just for example, we are going to look at the equation that we just derived. So that's why t del a square then y del t square equal to rho del a square y del x square, in this case del x square, and del t square, like this one. Okay, again the how we are going to find out. So y we will say separation variable px qt, and hence we will put it there. Finally, what will we get? We will get t over p del a square p del x square equal to rho del a square q over del t square rho over q. We get, and we find equal to c, right? Equal to a constant c. Okay, so let's call it minus c. Yeah, so let's call it let's equal to c, like this one only. Okay, and which will be positive or negative, we will see which will work. And the first equation becomes del a square p del x square equal to c over t times p, or minus this equal to 0. Okay, and second equation becomes del a square q del t square minus c over rho times q equal to 0, right? In both of them, the solution will be, the p will be, if you see the solution, will be sinusoidal. For example, for this one, sinusoidal when c is positive. So p equal to a sine omega t, right, plus, sorry, not omega t, but any we can propose basically in this case. So p will be again sinusoidal sine, we can say p equal to a sine alpha x plus b sine cos x, cos alpha x. If you put it there, what do we get? This will satisfy. Yeah, so this is going to satisfy in which case? When so we put it there, then what do we find out? So we find out alpha square, okay, minus c over t equal to 0. Yeah, and okay, and let us say in this case we have q equal to c, not, let's say, let's call it d1 sine beta t plus d2 cos beta t. This will be the solution for in this case. Yeah. Okay. Now, but in that case, solution will be when c is negative. So these are valid when c is negative. So c negative. Okay. When c is negative, then this will this is going to fit in there. Okay. Okay. So this value, if you put it here, then our values will be alpha square. We have minus alpha square here, right? And similarly for this, we will get minus beta square, minus c over rho equal to 0. Yeah. Okay. Now what we want? We want basically beta, in this case beta square will be since we put here beta already inside the sign, so we want beta to be a real number, and that's the only possible. Then C is negative. So B is square equal to minus C over rho, yeah, and we want C to be negative to work, right? Okay, and then it will work. Beta equal to plus minus root minus C over rho. This is going to work, yeah. And similarly for this also. If C is negative, then we get alpha equal to plus minus root minus C over T, like this one. So in both the cases, sinusoidal is the solution. Hence the general solution will be given by P times Q, right? So general solution you give as y equal to P x Qt, and hence the general solution you give equal to A sine alpha x plus B cos alpha x multiplied by d1 sine beta t plus d2 cos beta t. This is general solution you get. Okay, rest is applying the boundary condition and initial conditions, and you get the values for that. Okay. Now you can tell that when t equal to 0, everything is 0. Yeah, if t equal to 0, y equal to 0, that is only possible when t equal to 0. In that case, what you see is d2 equal to 0, and we get d1 will have some value. So if that is the case, so we go back here at these equations, right? So q will be something like we can assume q equal to sine omega t, because we know that this natural frequency will be here only, right? So this will be the natural frequency, yeah. So we can have instead of beta, we can replace beta with omega, and what we get here is t over p del square p over del x square equal to rho and over q, and then if q equal to this one, then del square q over del t square divided by q will be equal to nothing but minus omega square, simply. Yeah. Okay. So q will not be there. So means del square, if that is the given, then del square q over del t square 1 over q will be equal to minus omega square, simply. So you have rho minus omega square. Hence you have del square p or del x square equal to minus omega square rho over t times p. Okay. So this is this equation you get. Okay. So the next one from here, del square p over del x square equal to minus omega square rho over t p. Okay, so del square, then the solution p, we can assume p is equal to e to the power, again the p is also sinusoidal as we said earlier, right? So this will be as we said earlier, a sine alpha x plus b cos alpha x, right? So what do we get in that case? So what do we get in that case is, just see here, we get minus alpha square, right? We get minus alpha square in this case here, multiplied by p, right? That's what we will get this side, equal to minus omega square rho by t times p, and simply we get alpha square equal to omega square rho by t, and hence what we get in this case, omega square equal to alpha, omega square, or omega equal to alpha times t over rho. Right? So this is the natural frequency you get. This is the natural frequency. Okay. Now value of alpha, how will you get? You apply all the boundary conditions, like the way you got the value of beta in case of the beam vibration. In this case, value of alpha you will get from the boundary conditions. Yeah, you will apply boundary condition, you get value of alpha. It will give you in terms of this will be in terms of n. Yeah, so different n equal to 1 to infinity. So different n will give you different mode basically, right? The same kind of thing is also appearing here. But what we see here is omega is related to t, like higher tension will give you higher frequency, and lower, the ratio is important. That ratio will decide what will be the frequency multiplied by alpha. So this is what it completes. So this is just for example. We have solved for the string under tension. However, this can be applicable to all other kinds, like axial vibration, the torsional vibration, all be similar equations, and this is the string under tension. So similar equation, hence we solve similarly. Okay, so that is all. This also completes chapter number 7 from your e-book. Okay.